Hello everyone. Today we are going to discuss Bernoullis equation in fluid mechanics. For steady flow, the speed, pressure and height or elevation of incompressible non-viscous fluid are related by an equation discovered by Daniel Bernoullis. We are going to derive a mathematical expression for Bernoullis equation. So let us consider a tube having non-uniform cross-sectional area, and let us assume ideal fluid flowing through the tube. So I'm drawing let this be the ground surface. Okay, this is ground surface. Let ideal fluid, okay, fluid enters from this end of the tube. So this is called the input end. Okay, so this is the input end, and let us consider section 1 of the input end enters from section 1. Okay, and let the fluid leave from this end of the tube. So this is the output end. So we have ideal fluid entering from left of section 1 and leave the tube from section 2. Clear? And let us consider fluid initially contained between section 1 and 2 of the tube, and we apply work energy theorem to the fluid contained between section 1 and 2. So I'm writing, we apply work energy theorem to the fluid initially contained between section 1 and 2. Okay, so we have this, and let us call it figure 1. Now let y1 be the height of fluid entering at section 1, and let y2 be the height of fluid from the ground surface leaving at section 2. So we can see section 1 is at height y1. So the fluid entering at section 1 is at height y1 from the ground surface, and we can see section 2 is at height y2. So fluid leaving the tube from section 2 is at height y2 from the ground surface. And let v1 be the fluid speed at section 1 and v2 be the fluid speed at section 2. Okay, and let p1 be the pressure of the fluid entering at section 1, and let p2 be the pressure of the fluid at section 2. So we have this. Okay, now after time delta t, okay, the fluid will move, okay, the fluid contained between section 1 and 2 will move and will be contained between the section, let's say 1 dash and 2 dash, 1 dash and 2 dash. So after time t, the fluid contained between the section 1 and 2 will move and will be contained between the section 1 dash and 2 dash. Okay, so I'm drawing the same tube, okay, to give an idea of fluid contained between section 1 dash and 2 dash after time delta t. Okay, so this is the same tube. So this is same tube. Okay, so this is the ground surface. Now the fluid is contained between section 1 dash and 2 dash. So initially the fluid was contained between the section 1 and 2. Okay, we have this. So we have this. Now the fluid is contained between the section 1 dash and 2 dash. So we have this. Clear? We have this. So it is the same tube. Okay, so this is figure second. Just to give a clear idea of displacement of the fluid, so I'm redrawing figure 1. Okay, in figure second. Now what we find, let this length be delta x1. So after time delta t, okay, the fluid will be contained in this section, that is in between 2 and 2 dash, and let this length, okay, this length be delta x2. So this is delta x2, and we are taking incompressible fluid for which density, that is rho, is constant. Okay, so we are having this. This is density. So this is to be noted. So I have written after time delta t, the fluid will move and will be contained in between the section 1 and 2 dash. So what we get is that volume of fluid, okay, volume of fluid in section of length delta x1. So let me color this. Okay, so the volume of fluid in the section of length delta x1, okay, will be equal to the volume of fluid will be equal to the volume of fluid in section of length delta x2. So we find this, the volume of fluid between section 1 and 1 dash, okay, equals to the volume of fluid in between section 2 and 2 dash. So I'm writing in this form, okay, volume of fluid of section having length delta x1 equals volume of fluid, okay, volume of fluid in section of length delta x2. So we have this. Now we know density, okay, so let me do some rough work. So let us do some rough work, okay. We know density equals mass by volume, okay, and density in this case is constant, and volume of fluid in section of length delta x1 equals volume of fluid in section of length delta x2. So volume is constant. Therefore, we can write mass equals density times volume, and we know volume equals area times thickness, and let us denote thickness by symbol delta x, okay. So this is constant, so we can write in this way. Let us denote mass by symbol delta m. This equals rho and a delta x, and this is volume, okay, and let us denote volume by symbol delta v. So we can write in this way, delta m equals rho times delta v, where delta v is area times thickness, okay. So we have this. So this is area times delta x, and this equals volume delta v. So we have this. So we can write therefore delta m, which is mass, and this is constant. So let us write in this way, okay, using this relation. At section 1 we have rho, okay, because we know density is constant. So rho times A1 cross sectional area at section 1 A1 times delta x1, okay, thickness or length equals rho A2 delta x2, okay. This is for section 2, and we can also write in this way, this equals rho times delta v. So we can write delta M equals rho A1 delta X1 equals rho A2 delta X2 equals rho delta V. So we have this. Okay, we have this. Now, as I said earlier, we are going to apply work energy theorem to the fluid initially contained between section 1 and 2. Okay, so what we find, fluid is entering, okay, fluid is entering from section 1. So work must be done to push the fluid at the input end. So what we find, so let me change the color. So what we find, work must be done to push the entering fluid, because fluid enters from this side. Okay, so we have entering fluid to the entering fluid. So let me write in this way. Okay, W1, this is work done. Okay, this is work done at input end. So W1 equals, we can write W1 equals F1 times delta X1. Okay, so we have this. Clear? Now, this is work done on the system, because we use sign convention. Okay, we use sign convention and we take work done on the system as positive. So this is to be noted. Okay, so this is to be noted, and we know pressure equals force by area. So we can write W1 equals P1, okay, in this way, A1 delta X1. So we can write in this way. Clear? And we know this is volume. So area times length is volume. So let us denote this product A1 times delta X1 by symbol delta V. So delta V times P1 equals W1, and this is positive because it is work done on the system. Okay, that is work done on the fluid in order to push it at section 1, because work has to be done in order to push the fluid at section 1. So we have this. Okay, so let me write over here delta V, because we know volume of fluid at section of length delta X1 equals volume of fluid at section of length delta X2. So volume is constant, so we can write delta V. Okay, this equals A1 delta X1 equals A2 delta X2. So we have this. So we get this. Clear? Now, in same way, we find let me erase this. Okay, So we have to find work done, okay? Work done to push the emerging or leaving fluid, okay? Leaving fluid, because this is the output end, okay? We can see this is the output end. So fluid leave from section 2, okay? So work done to push the emerging or leaving fluid at the output end is, let's say, W2, okay? So this is what work done at output end equals, we can write in this way, F2 times delta X2, clear? And we can write in this way, okay? This is P2 A2, because we know pressure equals force by area times delta X2, and we know A2 times delta X2, okay? A2 times delta X2 is delta V. So this product is delta V because volume is constant, okay? So we have P2. So this equals W2, and this is actually work done by the system, okay? This is work done on the system. So for this reason, we are taking W1 as positive. So this is work done by the system. So by convention, sign convention, we take this W2 as negative. So we have this, clear? So we have W2, which is negative. Now we need to find total work done or net work done. So let us find net work done. So net work done, W equals, so we can write W1 plus W2 equals, so W1 is P1 delta V. So we have W2, which is minus P2 delta V. Therefore, net work done, W equals P1 minus P2 delta V. So we have this. Okay, we have this. Now, I'm erasing this, okay? Let me rewrite this, okay, over here. Delta M, this is rho A1 delta X 1 equals rho A2 delta X2 equals rho delta V, and net work done W equals P1 minus P2, and we have delta V. So we have this, okay? I'm erasing this. Now, this work done, okay? This work done equals change in kinetic energy and gravitational potential energy of the fluid of mass delta m, and delta m is given by this expression. Okay, so I'm writing in short, delta m equals density rho times volume, that is delta v. So we have this, and this is to be noted. Okay, now let us find change in potential energy. Okay, let us find change in potential energy of mass delta m. So let us denote change in potential energy by delta U, and we can write in this way. Okay, change in potential energy, we use this concept m g h. Okay, so delta m, clear, g, and h is height, so y2 is the height or elevation at the output end. Okay, change in potential energy is given by difference in potential energy at section 2 and section 1. So mgy2 minus, sorry, delta mgy2 minus delta mgy1, because section 1 or the fluid at section 1 is at height y1 from the ground surface. So this is change in potential energy. In same way, let us find change in kinetic energy of mass delta m. So let us find it. Okay, now change in kinetic energy, let us denote it by symbol delta E, and this equals half, we know kinetic energy is half mv square. Okay, this is potential energy and this is kinetic energy, so half delta m and v2 square. Okay, because fluid is leaving section 2 or is leaving output end with speed v2, so we have v2 square minus half delta m v1 square. Now we have this. Now from work energy theorem, okay, we know work done equals change in kinetic energy and gravitational potential energy. So we can write work done, that is P1 minus P2 times delta V equals sum of change in kinetic energy and change in potential energy. Okay, sum of change in kinetic energy and potential energy. So kinetic energy and potential energy, that is we can write in this way, work done equals sum of change in kinetic energy. So kinetic energy is represented by this. Okay, plus potential energy, change in potential energy is this, so we can write delta m g y2 minus delta m g y1. So we have this, clear. Now let us divide both sides. Okay, divide both sides by delta V. So we get P1 minus P2 at left hand side, clear, we get this, and we have this. Okay, half delta m by delta v, v2 square minus half delta m by delta v, v1 square plus delta m by delta v, g y2 minus delta m by delta v, g y1. And we can see delta m by delta v is the density. Okay, so we can write P1 minus P2 equals, so this is density, okay, this is density, this is density, this is density. So we can write P1 minus P2 equals half rho V2 square minus half rho V1 square plus rho G Y2 minus rho G Y1. Now let us keep all the terms, or let us arrange the terms in such a way that we have P1 term containing P1, V1 and Y1 at one side, and term containing P2, V2 and Y2 at another side. So on rearranging, okay, we can write in this way: P1, let us keep P1, okay, and we have this, and we have this, okay. So let me change the color. P1 plus rho G Y1, okay, plus half rho V1 square, okay. So we have this equals P2 plus rho G Y2 plus half rho V2 square. So this is the required expression, okay, and we have to generalize this. We need to generalize this. So we have this, okay, P1 plus rho G Y1 equal, plus half rho V1 square equals P2 plus rho G Y2 plus half rho V2 square. So we have to generalize this expression, okay. So on generalizing this expression, we can write sum of pressure. Okay, this is pressure, and this is, so what is this? This is rho JIWAN plus, okay, half rho. So we are generalizing it. So I'm writing in this way, okay, dropping 1 and 2, okay, plus half rho V square. So this is constant, okay. So we have this. So this is Bernoullis equation, okay. This is Bernoullis equation for steady, okay, for steady, non-viscous and incompressible fluid. So we have this, okay. Now let us divide, okay, both side by G. So we divide both sides of this equation by G. So what we get from this equation, okay, P by G. So we have this plus rho GY divided by G plus half rho by G V square, and on left hand side we have constant by G, and we know G is constant, okay. If we take G constant, because we know the value of G is constant, so we get constant again. So we have this, okay, we get constant. Now this cancels out, clear. So we are left with P by G plus rho Y plus half rho V square by G equals constant, clear. We have this. Now again let us divide by rho on both sides, okay. So what we get, dividing by rho on both sides, because we know density is constant, so we get constant on right hand side, and we have this P by rho G plus Y, okay, plus half V square by G. So we have this, okay, and this term is called, okay, this is called pressure head, okay, it is called pressure head, and this term, okay, it is called gravitational head, gravitational head, okay, and this term, okay, this term, okay, this term is called velocity head. It is called velocity head. So sum of pressure head, gravitational head, and velocity head is constant, okay, for steady, non-viscous, and incompressible fluid. So this is to be noted, okay. Now let us do some cases, okay? If fluid is at rest, because initially we have considered fluid in motion. So if fluid is at rest, then V1 equals V2 equals 0. So from this equation, okay, so from this equation, what we get? P1 plus rho gy1 equals P2 plus rho g y2. So we can write P1 minus, we can write in this way, P2 equals rho g is common, okay, y2 minus y1. So this is y2. So we have this. So we can denote y2 minus y1 by symbol h, and this is the difference in height, okay. So this gives difference in height, okay, this is difference in height. So therefore we can write P1 minus P2 equals rho, that is density G, and we have H. So we can write or rewrite Bernoullis equation for fluid at rest by this expression.